Okay, so we've derived the formula for continuous compound interest. We have a equals p times e to the rt, where we found e is the solution to our limit here. And here I replaced h with n. H is really a dummy variable, so I can use any variable that I want. And by convention, most mathematicians will use n. So in this case, this n could still be thought of as compounding periods going to infinity. It's not exactly accurate, but it actually gives us the same answer, so it doesn't matter. So by convention, I'm just going to go back to n. So the limit as n approaches infinity of 1 plus 1 over n to the n. And so in order to find the value for e so we could make this formula worthwhile, we have to somehow compute e. And right now, this is the only formula we have, so that's all we have to work with. Well, we saw a couple of things about e. First and foremost, it's a strictly increasing sequence. That is, as n gets bigger, the value that I calculate here will continue to get bigger. So to find a representation for e, I just need to put in bigger and bigger values for n. And then I'll get closer and closer to the actual value for e. The other thing we know about e is that, at least using this formula, we can't find it exactly, simply because to get it exact, we have to take n to infinity, which is obviously not actually possible. Again, infinity is not a number, it's a direction, it's a thought destination. I'm going towards it, and I'm never going to stop. So this formula will never get me the exact value, but that's probably okay. I just need something close to it. So let's put in a few values for n, and let's get a few approximations for e. So let's say I want to find the nearest whole number for e, the whole number value, so that I plug in a value for n, and when I round it to the nearest whole number, I get the closest one for e. Well, it turns out, plugging in for n in this formula, I can't be any smaller than 6. So I start with let n equal 6, and if I plug that into this formula and then round to the nearest whole number, I'm going to get that e is approximately 3. So 3 is the nearest whole number representation of e. And that's not going to be very accurate. We're going to want a few more decimal places than that, but that's just kind of how we get started. All right, so now let's say I want 1 decimal place of accuracy for e. Well, to do that, n has to be at least 19. It turns out that if I want 1 decimal place of accuracy, I can't be any smaller than 19. And when I plug that in, and then round to 1 decimal place, I'm going to get e is approximately 2.7. Let's keep going. Let's go to 2 decimal places. All right, well, I want it to be an accurate 2 decimal places. So in this case, in order to get 2 accurate decimal places, I have to let n equal at least 414. That's right. To get 2 accurate decimal places for e, I have to go as high as at least 414. That's huge. I don't know about you. Even at 19, I wouldn't want to calculate this by hand. Actually, I really wouldn't want to do it with 6 either, although I probably could. I do get bored sometimes. But 414, I'm not that bored, and I don't think anyone should be. So what we're showing right now is that e is basically not going to be possible to calculate with any degree of accuracy without a computer or a calculator of some sort. But as of right now, that's all we've got. So what does this tell us? This tells us that e is approximately now 2.72. Okay. But I wouldn't get that until I hit 414 for n. At 413 or less, this won't round to 2.72. It'll actually round to 2.71, which is less accurate. This is the more accurate representation. Let's keep going. All right, I want 3 decimal places of accuracy. Now, before I write it down, take a guess. Look at how fast these grow. What do you think it might be? Turns out, 1,738. If I want to get 3 accurate decimal places for e, n has to be at least that size. So I plug that number, or greater, into our formula here and round to 3 decimal places. And I'm going to get e is approximately 2.718. Let's go one more. All right, I want 4 decimal places of accuracy. Again, think about, look how fast these numbers are growing here for n. What do you think it's going to turn out to be? And I have to admit, I was really surprised when I found this one too. The answer is 42,702. That's right. Anything less than this plugged in for n and rounding to 4 decimal places will be less accurate, or relatively speaking, inaccurate. To get it as close as possible, I have to be at least that size for n, and this tells me then that E is approximately 2.7183. And again, that's rounded to 4 decimal places. To go higher than this, n has to be greater than 100,000. And I don't even know the next value. My calculator goes into overflow mode and says I can't calculate it beyond that. All I know is that it goes above 100,000. So that tells me, again, that if I want 5 decimal places of accuracy for E, I got to reach some number that I just can't calculate. So, although I know E exists, and I have a sort of approximation for it to 4 decimal places, I can't go any further, at least not with the computation tool that I have at my disposal. And so, although I can, again, get an approximation for E, it's not very accurate, and it's not telling me very much about this value here. And so what I'm going to want to do is want to explore, is there a better way to evaluate E, or to represent E in a different kind of formula? Now, in order for us to go there, we're actually going to need a few more tools at our disposal. So over the course of the next few videos, we're going to be covering other mathematical things that we're going to need before we ultimately return to E so that we can learn more about it. But in the meantime, we have since found accurate values for E. And so we're going to use those values, which you can find on your calculator, and we're going to explore how the continuous compound interest formula compares to the compound interest example we were using in the previous videos. In the example from compound interest, we said the amount of money borrowed, or the principal, was $10,000 at an interest rate of 10% per year, a number I chose just to make the math a little bit easier. A little high in reality, but the principal remains the same, excuse the pun. And we left off with, what if we compounded the interest monthly, where we said n equals 12, and these were the values that we computed for t equals 1 through 5 years. And now let's compare that, the highest rate we had shown returned through that example, with continuous compound interest, that is, as n approaches infinity. And so we can see the differences here between each of these compounding 12 times to continuous compounding interest for each of these years 1 through 5. And as we can see, in the first year, it's only an increase of a little over $4.50. In this second year, it's an increase of just under $11. If we go down to the 5th year here, we can see it's an increase of about $34, just a little bit more than that. So not a large increase. Over 5 years, compounding monthly versus compounding infinitely, continuously compounding, I'm going to get about $34 more. So that's not a huge increase. And it's the reason why we don't see a whole lot of realistic scenarios involving continuous compound interest, simply because, well, first of all, there's a lot of rounding, with E being a number we don't have the exact value for, as well as there's not enough profit to be shown for it. But at least we can see that this would be the maximum amount earnable given these scenarios here. And then there's one more thing we can say about E. As I look at the formula for E in this limit, and I pay attention to just what's in the limit, it's very, very similar to the compound interest formula with just a few missing pieces. So let's take a look at what that looks like. The compound interest formula was A equals P times 1 plus R over N to the power of NT. And what I want to do with this is take a look at what I have here and see how it matches up with what I have here. So the first thing I look at is P. P is what I'm multiplying by my parentheses. Well, right here, what am I multiplying by my parentheses? Well, I don't see anything. And so, of course, when you see nothing, we say that means it's a 1 when you're doing multiplication. So it's really like there's a 1 right there. So I could sort of say, in my calculation for E, I can think of it as P equals $1. And then as I look in here, I've got R, and up here my R is a 1. Well, R is an interest rate, and so I would say what percent per unit of time is represented by 1? Well, that's the same as 100% per year. So I can say, all right, so it's kind of like saying R equals 100% per year, a very outrageous interest rate, but a number nonetheless. And then I've got N in place and N in place. And then I've got an n up here and an n up here, and then I've got t right here. So what am I multiplying by n? Well, again, up here there's nothing, and so in multiplication it means I'm multiplying by 1. So I can think of this as t equals 1 year, and then of course I'm taking n to infinity. So the other way we can think about the value for E is to say take $1, invest it at an interest rate of 100% per year for 1 year, and compound that interest continuously. The amount of money you have at the end of that 1 year, that's the value for E. Now obviously in money we're going to round to 2 decimal places, which we saw accurately was 2.72, and so we could say we get approximately $2.72, which means that's what E is approximately. But if we don't do any rounding, we found that when we went to 4 decimal places, it's about 2.7183, and we also know it keeps going from there. And so ultimately we want to find where does it end up, but before we get to that we'll be doing other videos. But of course in the meantime, you watched it, you can't unwatch it.